Anaerobic digestion. You probably know it's a process that involves microorganisms that degrade organic matter, break it down into a number of materials in the absence of oxygen. Products of this digestion include energy-rich biogas, which can be used, for example, to generate heat, electricity. There are solid and liquid effluents as well, which, given the proper treatment, can be used for beneficial applications. Anaerobic digesters were introduced some 50 years ago, but it wasn't until about the mid-90s that there was greater interest in them, and they were used primarily at the time to treat agricultural waste. But in the past decade or so, the interest has grown enormously. In fact, the American Biogas Council states that there are more than 2,300 sites producing biogas in all 50 states. And of these, more than 1,250 sites use anaerobic digestion as part of their wastewater treatment to reclaim water. Our speaker, Theo VanAken, has a bachelor's degree in biosystems and agricultural engineering from Michigan State University. Theo is the superintendent of the Holland area water reclamation facility. He's been with the Board of Public Works for 8 years, and for the first 6 years of that time, he was a planning engineer responsible for engineering activities and project management for capital projects in various utilities under the umbrella of the Board of Public Works. Theo last spoke to House members in the fall of 2020. At that time, he explained why the addition of an aerobic digester was necessary to reclaim water in Holland. Today, he will discuss the finer points of this large-scale digester, which is now in operation. Please join me in welcoming our guest, Theo VanAken.
Just thank you, everyone. Can you hear me all right? Volume is good. Wonderful. We'll get right into it. Thank you, Louis, for the nice introduction. Basically covering the same things here. Biosystems engineering, for those that are unfamiliar, is really an offshoot of agricultural engineering, is what that degree would have been called in years past, but a lot of environmental focus. I have a professional engineering license, so that's a license through the state of Michigan, just proving that I, can meet the requirements of being an engineer. My focus is in environmental, so wastewater treatment is certainly part of that. I have experience working in food processing, working in agriculture, with anaerobic digesters, as well as other treatment projects for that, and then with the municipality. Now, I've been the superintendent for 8 years, but I was also with the board for 6 years prior to that as a planning engineer. So got a fair amount of experience across all the different departments of the Board of Public Works, but certainly enjoy my time working at the water reclamation facility. See a picture here. This has been my newest project. That's Josie. She's 8 months old, almost 9. So if I am a little hoarse, I apologize, but I'm not sleeping much, and she's in daycare, so I'm sick all the time. So, but nothing bad, or I wouldn't be here, I promise. This is always just a lovely picture of Windmill Island here, the windmill, and just kind of want to talk about what I'm going to be going through today, because I always say, you look at this beautiful shot and you turn about yay far and you're looking right at our plant. So that's a lot of the background of this facility, is that we're right here, we're right downtown, we're the neighbors to everyone in this area. So we need to be very cognizant of how we treat our neighbors. Now, the agenda today, we're going to go through kind of some of the background of the facility. We'll stay light on that because we want to focus mostly on this project. We'll drive into why we did this. There will be some discussion on PFAS. I know there's been a lot of interest in that lately, and that does have a lot to do with the treatment of our solid portion of our wastewater as well as the liquid portion. We'll talk a little bit about biosolids, what they are, and what we can do with those. We're going to go through the project, how we did the project, and what the drivers were. We'll go through Envision, which is a certification that we followed framework when we did this project, and then where we are at currently. So we'll get right into it. Holland BPW, pretty much everyone here I think knows what we are. We are your utility provider. We do electricity, water, broadband, wastewater, and we take our mission and vision very seriously, that we are here for you. You are our customers. It is our job to provide, good utility, reliable, affordable, sustainable utility services. Another big driver that we follow is a community energy plan, which is developed with the city of Holland with the goal of reducing our carbon output per capita to 12.25 metric tons by 2030. Now, this is updated every 3 years or so. And this project is a really big part of that, because we were able to offset a lot of our carbon impact by creating this renewable biogas and reducing the amount of solids we have on our site. We'll get into that as we go, but this certainly plays into this project. Waterfront Holland, another big one as well. Our location is more or less right on the water. We know that the city wants to develop the waterfront, and we need to make sure that we can continue to be a good neighbor so that people will want to live and visit, here in Holland. These plans are just different plans that were set up over the years for the waterfront, envisioning of what it may be. And a lot of this has, there's a lot of desire for public access all around our facility. And so we need to ensure that what we do is a benefit to that. We don't want to be really odorous. We don't want to have a lot of dangerous truck traffic, things such as that. So this project really played into the Waterfront Holland as well. Now, like I said, I want to be light on the wastewater treatment plant itself, but feel free to jump in and ask questions at any time. I like to keep it fairly informal. But wastewater treatment we're receiving into our facility is going to be the domestic sewage, which comes from normal bathroom, kitchens, showers, waste. Then we have what we would consider non-domestic wastewater. So that's going to be commercials. It could, so it would be restaurants, stores, the industrial, those are really big impacts on us as well, because we have some very large industries here in Holland, which is a wonderful thing, but they produce a lot of wastewater. So that's something that we have to take into account. We also have what's called infiltration and inflow, and that is basically clean water that finds itself into the sewer system, which then comes to our facility. Infiltration and inflow, the problem with it is that it doesn't need to be there. It's usually rainwater or groundwater, and it doesn't need to be treated by our facility to be safe in the environment. So we try to keep that out as much as possible. And we do that through sewer replacements, sewer lining projects, ensuring that if certain houses built, a lot of them in like the 1970s, often had their sump pumps in their basements connected to the sanitary sewer. So we don't want any of those connections, because one house could send us, 200,000 gallons of water if we had a big rain event and there was, water coming into the basement. That water is safe to be discharged outside the home or into the storm system. So that's the idea with trying to limit the infiltration and inflow. And the city and the townships as well have done a good job at helping with that. So all that comes into our facility, and at the end of the day, the two main products we're going to have are the clean water and the biosolids. So we're separating those out more or less. So the clean water goes off into Lake Macatala, and the biosolids are handled differently. This is our site, and this is just right off of Google Earth. It's a pretty accurate photo, pretty new. So I'm going to try and use the laser pointer here just to show some of the bigger process points of the facility. So we receive wastewater from the City of Holland, Laketown Township, Fillmore Township, Park Township, and Holland Township, divided into what we refer to as a northern and a southern service area. The southern service area is managed by the Holland Board of Public Works, and the northern service area is handled by Holland Charter Township. So they own the sewers, but it all comes together into our facility. So from the south, everything comes in on a gravity sewer down Central Avenue, and then comes in and then is pumped up to our headworks. The north side is pumped directly to our headworks facility, where we screen out large debris. It could be rags, it could be construction debris, gravel. We get a lot of things in the sewage, so we try and screen all of that out before it goes into the treatment process. The treatment process consists of primary and secondary treatment. Primary treatment are these 4 covered tanks here in the upper right corner. For this side here, there. And that is using basically a wide spot in the line where the flow slows down and density will do its work. So any fats, oils, or greases will float to the top, anything heavy settles to the bottom. We take the clarified water from in between, and that's gonna do about 50%, I usually say on average of our treatment, is done in the primary step. From there, it goes on to the biological stage, which we call secondary treatment. Secondary treatment exists at our facility on both sides of River Avenue. So we have 1, 2, 3, 4 tanks there, and then there's actually 5 tanks right here. For this side, we have our 1, 2, 3, 4 tanks, and then the 5 tanks on the west plant. In that, we're using aerobic bacteria that utilize oxygen to break down the pollutants, and they consume it. And then they go into our secondary clarification stage, which is functionally the same as our primary clarification stage, which are these 2 round tanks and these 4 round tanks here. And what's happening there is the bacteria, after they are done consuming pollutants in the wastewater, they will settle to the bottom of those tanks, and we're able to remove them from the stream. And then there's kind of where we get our split between our solids and our liquid. So then the water is disinfected. We use sodium hypochlorite, so a very strong bleach solution. And then we neutralize that bleach and it goes into Lake Macatawa at the old James D. Young coal-fired power plant site, for those of you that are familiar. So basically, right straight out here, we go right out west to the river, right here. We will be updating our disinfection system to use an ultraviolet process, and that process doesn't use any chemical, which is really nice. Bleach has become very expensive and hard. There, during the pandemic, it was hard to get a hold of, so we can use ultraviolet light, like a light bulb basically, to neutralize and make it so the bacteria and viruses can't reproduce. The ultraviolet,
Question, please.
yes, the ultraviolet system will come online, should be within the next 2 years. We're almost done with the design, and it's gonna go out for bids this winter. But yeah, once it's open, everyone, we love to have tours, so we can certainly have folks out to actually come and see and smell everything, and have fun. We have a good time out here, and we really like what we do. Now the solids are all coming together, and they're gonna go into our anaerobic digester. So all of our solids handling is gonna be over here on the east side of the river. So there's a digester, this is our solids handling building. And then we've got solid storage tanks here right along 3rd Street. So they're the storage tanks, the digester, and then the solids handling building there. So we do all this treatment, and why do we do it? Because we don't want to negatively impact the environment or public health. Those are really our 2 big drivers. And those, we work with State of Michigan, EGLE, which stands for Department of Environment, Great Lakes and Energy. It used to be the DEQ, it used to be the DNR, it was a DNRE. It changes every 4 to 8 years based on what governor is in charge. But basically what they're doing is they're taking the rules from the EPA and they're helping us, they're developing a permit. So this is very small, you don't need to necessarily read this, but this is a page out of our permit. And it's called the National Pollutant Discharge Elimination System, or NPDES. The idea here is that EGLE will look at our receiving water, which is Lake Macatawa. It'll look at the constituents in our wastewater, and they will develop limits that we cannot exceed. So that helps us design our process and operate our process in a way that all of our pollutants that are discharged are below those limits. So that way we don't have any negative impact on the lake or on public health. Another really big part about what we do, and it comes a lot into play with biosolids and the anaerobic digester, is what's called the Industrial Pretreatment Program, or IPP. Also often referred to as pollution control. In my industry, we have to have 10 names for every single thing. The idea behind the IPP program, or I should really be the IPP, is that the industrial customers, we call them significant industrial users, SIU, they have a big impact, as I mentioned. So each person in this room is going to discharge on average about 100 gallons per day of wastewater. The BOD is going to be like 250 milligrams per liter. BOD is biological oxygen demand, which is one of the pollutants that we track and treat for. But in industry, they may put out, we have one on the north side, they're doing 700,000 gallons a day, up to 1 million potentially. So you can have, and some of the waste streams can also be very concentrated, so they can be really strong. So while our wastewater from our home might be 250 milligrams per liter, industrial wastewater could easily be in the thousands, if not tens of thousands. So it's the industrial pretreatment folks, his job to track and to work with all these industries and ensure that they understand what we can handle at our site. Because I wrote here, we've got what we call compatible or toxic pollutants. The compatible pollutants are the ones that we treat for. So those ones we'll put a limitation on. We also will surcharge these customers to help them pay their fair share. So that way you and I are not subsidizing, a company that's sending a lot of loading to us. We've developed, worked with some financial folks that can say, all right, it costs us, I forget, $2, say, to treat a pound of BOD, or it costs us $4.50 to remove a pound of phosphorus. That will then be charged to that customer because they're discharging that much extra to us. So they don't get charged extra for the base that everyone is doing, like this was a place that only, an office building, for example, that only had just a break room and bathrooms. They're not going to be surcharged because they're not sending us anything stronger than what you or I might send down our drain hole. Very importantly as well are these toxic pollutants, and these are ones that either they pass through the facility or they cause toxicity. So we have bacteria, we need to make sure they stay healthy. So we need to keep good tracks on those. So that can be heavy metals. Benzene was an example from years past. PFAS, that's the big one right now, and I'll dive a little bit more into PFAS here as we go forward. We have 3 people that work on this endeavor. We have 2 technicians that are out sampling and inspecting 5 days a week, and then we have our supervisor for that as well. I mentioned about for the SIU customers, what they can discharge. That's what we call the local limit. So a local limit, these are site-specific discharge standards. So that is, we basically will go through and we'll work with a consultant and we'll look at our facility and say, this is how much we can treat or handle of each pollutant. And you look at your biosolids, you look at your effluent, you look at several different things and you pick the most stringent, like this is going to impact biosolids more than your effluent. Okay, so we're going to set this limit lower. So that allows us to make our own, similar to what the state of Michigan does for us in our permit. We're going to issue a permit more or less to these customers, and they're going to be expected to stay below these local limits. And if a customer cannot treat their pollution to that lower level or remove it, they either need to haul it away to someone who can, or they need to install a pretreatment system to remove the pollutants before it goes into the sewer. This is all very important because of what it can do to our site and to our anaerobic digester. Just so y'all can see, this is what we're actually doing out in the field. These are samplers. It's there with a number 2 on it here on the left picture. That actually fits inside a manhole and it hangs there. And there's a tube inside with a pump, and that pump's going to grab it. We can do it by time or we can do it by flow if we have a flow meter, but it's going to grab continuous samples over a 24-hour period. And then our folks will go and then we'll take the sample out of the carboy every night, or every day, I'm sorry. So then we got an entire day's worth of flow in that sample. So we're able to check it and make sure that nothing bad came in. And that helps with the industries. We don't have any industries here that are not trying to do the right thing. They really are. They work with us very well. We have a lot of respect for them and they for us. But you never know what person you may have working on 3rd shift, that needs to get rid of something, and they might just dump it down the drain. Well, this is a way that we're able to capture that and ensure that, the sewage stays safe. So kind of along with all this, there's some requests for a little bit of information on the PFAS issues. And we've been dealing with PFAS at our site back from 2018 is really when the state of Michigan came to us and asked us to start looking into PFAS and checking our customers to see what we have coming in. The PFAS themselves, it's really they're synthetic organofluorine chemical compounds. And the main idea is that they repel water. That's the beauty of them. They repel stains. Scotchgard is a PFAS. Teflon was a PFAS. I believe a lot of these have been reformulated over the years. But back in the 1930s and 40s, these chemicals were first developed, and then they really were put out into the world in the 1950s and 60s. Some of those raincoats that are super thin, were coated with PFAS, or even tents, food wrappers, lots and lots of things. And then we come to find later that, well, PFAS is not really good for people. It has a lot of health risks. Health risks are, it's carcinogenic, it's an endocrine disruptor. I've got a whole list of things here that it can do to you. It's kind of not great, but found to cause kidney, prostate, testicular cancer, ulcerative colitis, thyroid disease. Oh goodness, so many things. So, unfortunately this wasn't found out beforehand, but now that we know, we need to do something about them. So we have to start looking for these chemicals. And the thing with PFAS is that they're very resilient. That's one of the beauty of that chemicals. It's hard to get rid of. It's a forever chemical is what you'll hear them referred to as, because just left inert in nature, they're never going to break down. That fluorine bond is very, very strong, and it's going to hold together. So it has to be treated. It can be treated in a few different ways. The main way is to remove it at the source in like an activated carbon filter, similar to like a Brita filter. That would remove PFAS. But in 2018, Eagle comes to the wastewater plant and says, okay, we need to figure out what kind of issues do we have around PFAS. So we sampled our influent, we sampled our effluent water coming in and out of the plant. And then we went out and we identified potential customers that might be sources of PFAS. So we went and tested. Honestly, we just tested all of them for the most part, because it is everywhere. The places where it was found in higher concentrations would be like aqueous firefighting foam, AFFF, you'll hear that. That was a PFAS chemical because it held foam really well and suppressed fires. We don't have any of that here, but they found even sites where they had to use the AFFF to put out a fire, that PFAS is still there. So it'll still be contaminating the site and it can end up in the drain. We didn't have any of those scenarios, but we did find a metal finisher, because it also can be used to keep the metal finishing chemicals from volatilizing out of tanks. So it would be put in as kind of like a coating that would float on top of the other liquid. And the one customer, they had not been discharging their processed wastewater to us since like 1992. But even in their domestic wastewater, since it was going through the same pipe, there was still PFAS in that pipe. 30 years later, it was still there. So they had to go through and do a really intensive cleaning to get it out of there. Another source that we found was a factory that was filling spray paint cans. And at one point in time, they were filling spray paint cans with Scotchgard. So they had a lot of PFAS contamination in their groundwater. Fortunately, the groundwater was already being collected and treated. They just had to add the additional step of the carbon filtration to that. But the big benefit for us is we definitely had good cooperation with our customers. We didn't have a lot of PFAS in our system compared to some areas, so we do count ourselves fortunate. Interesting things about PFAS for like the sampling side is there isn't even a true testing method that is approved yet. So whenever we run a sample in our lab or any other lab, we have to use a test method that is approved by the Environmental Protection Agency. And it's more or less so that they can say that, yes, we have confidence that these results will work if you follow this method. For water, there are approved methods for PFAS testing for drinking water, but for wastewater and soil and biosolids, there are not. So we have 3 different methods that we can use. There's 1633, 537 modified, and then ASTM DNet 7979. The 1633 is going to be the law of the land once the EPA gets around to, it's called promulgation. So they've reviewed it, they've agreed that it works, but they have not promulgated this rule yet. So it's not out there, like we can use it, but we don't have to use it. We're allowed to use any 3 of these sampling methods, or testing methods, I should say. One of the benefits of 1633 is that it covers 40 different PFAS analytes. So there's thousands of them, but the other ones only do 28. It still is better than what we need for now, but eventually we will move to the 1633 and all the testing will be done under that. I say cross-contamination can be a big concern. It hasn't been as bad, but you do have to be really careful because a lot of things we're testing in the parts per trillion level. So this is like unfathomably small volumes that they're testing for these PFAS. So you don't want to be wearing waterproof clothing. You don't want to have fast food wrappers. You want to be careful about even using dental floss because a lot of this is not as much of an issue now, but when we first started, people didn't know. So a lot of these companies were using PFAS chemicals. So state of Michigan provides a lot of guidance for us. They're very good to work with. So we can go online and make sure that we're using the proper chemicals, that our technicians are grabbing the samples properly so that we have accurate numbers. For interest here, so drinking, this is Michigan water quality standards for PFAS. This is really the rule for these chemicals of what we need to be maintaining. So this is saying like Lake Macatawa should not have, it's a non-drinking water source. So that's going to be this column here on the right. But you want 12 parts per trillion or less of PFOS. PFOS and PFOA are the two that we're most concerned about. So these are the numbers when I look at wastewater coming in, we need to be well below this. But there's a few different ones. So for drinking water, they're looking at more, which is more important because drinking water goes directly into our bodies. For what's going out, we're looking at PFOS, PFOA. We are analyzing for all 28 or 40 different analytes. And we do submit that to the state of Michigan, but the PFOS, as we call it, and PFOA are the two most important. Now, the biosolids, which is the solid part of our waste stream that's going into our anaerobic digester, as I mentioned, the PFOS and PFOA are the two that we're really tracking closely. So we do get the entire 28 analytes and we submit that to the state of Michigan every year. But what we're reporting out is really focusing on the PFOS and PFOA. The state of Michigan has set these thresholds for the biosolids. So we're looking at 100 nanograms per gram, and that's in parts per billion. So that's still really small, but not as small as parts per trillion. And it's really because this is a solid portion. When you're looking at in the liquid, it's in a volume. We're switching it over to the solids when we talk biosolids. If we have 100 nanograms per gram or more of PFOS or PFOA in our biosolids, it's going to be industrially impacted, and that means we can't land apply it. Lapeer was the city that ran into this the worst. They had some they're well into the hundreds, if not the thousands, and they had a metal plater that was discharging incredibly high amounts of PFAS to them. So this number originally was 150, and it went down to 125, and now it's gone down to 100. And we expect that number for limiting the land application of the biosolids, which we'll talk a little bit more about here. It's because we're getting it out of the system. All the wastewater plants, we've done our research, we've met with our customers, and we're requiring them to remove the PFAS from the sewer in the first place. So you'll start to see these numbers tighten down, and that's really good news. That's proving that, yes, we are successfully getting rid of the PFAS. Because everyone wants to be at the lowest level here, below 20 parts per billion. Then you don't have any issues with land application as far as regulations go. Probably most important for us here are what are our PFAS levels at our facility. Our final effluent, which is the water going out to the lake, very small numbers, 3.22 nanograms per liter. And then we've got 4.92 nanograms per liter. So those are parts per trillion. Those numbers are well below what the state is looking for. In the biosolids, we're below 10 and below 5. And these numbers are actually higher than what I'm used to seeing. I'm used to seeing less than 2.00. And the reason why is we actually tried that method 1633 for the last time we ran the biosolids. And the lab, it's a new method, so the labs aren't quite as good at doing it, so as they get better, we're going to see these numbers come back down. So when we used the 537 modified, we're getting at the most maybe 4 or 5 parts per billion, and to see that 10 was kind of shocking until I talked to the lab, and it was kind of a training thing on their part. But 10 is still good. It's less than 20. We're doing well there. So these meet what we call an exceptional quality class A. So they are very clean and very safe. We do sample for our final effluent for PFAS 4 times a year on a quarterly basis, and the biosolids are done once per year before we start on land applications. So I've done a lot of talking about biosolids, so I should probably tell you what they are. This is a picture. This is more of a dewatered, thickened up biosolid in this hand. It looks a lot like clay or soil, but basically it is the solid portion that we have left after the wastewater treatment process. So it's going to be the solids that come off the primary clarification step, the solid to the bottom of the tank. It's also going to be the bacteria that settle to the bottom of the secondary treatment tanks. We collect fats, oils, and grease as well, and that can be treated as a biosolid, but right now ours are actually going to a landfill. They're just being concentrated, thickened up, and then sent to a landfill. In the future, we'll look at doing the oil potentially in the anaerobic digester, but we're not doing that currently. There are generally 3 different ways that one can dispose of biosolids. So there's the land application, which is usually known as beneficial reuse. So it's used as a fertilizer. We can landfill it, which just gets it, it's put in one place where it can be tracked and watched. But if we landfilled all of our biosolids, the landfills would be full up pretty fast. So we don't like to landfill if we don't have to. So we really try to focus on the land application. And your third option is incineration. Incineration has some air permitting challenges, but it can be done. We have done it here before, back in the 1970s. And there are sites out there that do incinerate, but it's high heat, a lot of moving parts, a lot of operator intervention. It's really best, in our opinion, if we can do the land application as much as possible. So biosolids are wastewater, right? They are coming down the sewer, so that stuff is generally not safe. So how do we make it safe? We do a lot of monitoring. We have the IPP, so those folks doing the sampling to ensure that the industries are not negatively impacting us. We also are making sure that we need to check the nutrient levels of all the biosolids. We need to look for pollutants, so we're tracking PFAS, we're tracking heavy metals. We need to know that if it goes out into the environment that it will be safe. We also are monitoring the fields that we would land apply them to. Now, if this goes off to a landfill, we don't need to really worry about it, because then the landfill accepts responsibility for it and it goes into their leachate collection systems, and there are no concerns with the disposal at that point, at least on our end. But if it goes to a field, we need to ensure that we don't overload the field. You put too much nitrogen or too much phosphorus, more likely in this area on a field, and the crop doesn't uptake that, it'll end up running off, it'll go into the river, it'll end up in Lake Macatawa, and then it's, unfortunately bright green for August and September of most years. So we do a lot of tracking. You don't just go and put it out willy-nilly. You need to actually look at that field. You need to know what crops are going on it. You need to know what the nutrient levels are before the crop goes in, and then you need to know how much nutrient the crop will have. So those are all taken into account when we land apply our biosolids. Water table depth is very important. It needs to be 30 inches or lower, because we do subsurface inject the biosolids, so they go about 6 to 8 inches underground where the crops can really uptake them. But you don't want the biosolids getting into the groundwater. You also don't want it getting into any sort of runoff conditions, so you have to be careful with slopes. You need to have setbacks from wells, from streams. Lots of things come into play when we're looking at land applying biosolids. We're going to treat. So we don't just send it out right from the tanks. Similar to the effluent water is disinfected, we do a similar process with the biosolids. So we have a Class A or a Class B standard, which I have a little bit more information on here coming up. There are rules and regulations we follow. There's EPA federal, there's state of Michigan. As I mentioned with the NPDES program or permit, the biosolids are part of that. So it all is coming into the same exact umbrella under the EPA and through Eagle. And by that, we have to develop what's called the Residuals Management Program, so the RMP. The RMP is an agreement between us, the generator of the biosolids, and the state of Michigan, so Eagle, as to what can we do with those biosolids at the end of the day. So that we tell them how we would like to treat them to meet a Class B standard or a Class A standard, and they'll agree with that. We also have to worry about what's called vector attraction. So that would mean if you sprayed a bunch of solids on the field and birds showed up or rats showed up, those vectors can then get contaminated and then move off site and then potentially hurt somebody or make them sick. So we have vector traction issues, so that's why we subsurface inject, that takes care of that. When I talk about pollutant ceiling concentrations, why that is set in the EPA regulations. So the classification is a Class A or Class B. And what we're saying is how safe it is to contact other humans. So this is really a public health thing, more so than the environmental health. The environmental health is when we look at setbacks in the pollutant loading, or not pollutant, but nutrient loading and such. But the Class A, conceptual quality, is going to mean there's very low metal content, very low PFAS content, and there are no detectable human pathogens in this stuff. So you can take the Class A biosolids, you can take a bucket of it home and dump it on your garden, on your yard, your golf course, wherever, and it'll be safe to do so. You won't get sick by it. Class B biosolid, they can have trace amounts of pathogens in them. And the way that we control Class B biosolid is all by site control. So when you land apply, you're going to subsurface inject it. It's going to go on before the crop, and then no one's going to be allowed to access that site for 30 days. Like the public, it's not going to be allowed to access the site. And you have to do the vector attraction reduction so that anything can't leave. So that's how Class B is handled. So that way, by the time the crop has grown and done its thing, there's going to be nothing active in the soil at that point in time. You'll only have the nutrients and the organic matter and such, but you won't have any pathogens. It doesn't go on to any direct human consumption crops. So you're not going to put a Class B biosolid on a blueberry farm like we have here in town, but you would put it on a cornfield that's going to be either a cattle feed or hog feed, or soybeans that may go to oil production, because there's not going to be any sort of direct human contact there. So if you were to take, say for example, there was a human pathogen that didn't get killed during the Class B process, put it in the ground, and it found its way onto the corn. Corn's eaten by the cow doesn't get the same illness as we do, so that can break the chain right there. Now Class A, a lot of us may be familiar with the middle, Milwaukee's, which is Milorganite. Milorganite's been around since I think it was 1919, if I recall right. It's been a while. They use a dryer to get to their Class A status, so that, and anyone that's used this, it's a very granular, dry product. I've put it on my lawn before. A lot of benefits. It's very slow release nitrogen fertilizer. Farmers love it. Golf courses love it. You can get 3 years worth of nitrogen release out of one application of a biosolid product. Chicago has their EQ compost, they call. Washington, D.C. Out west, you've got Tacoma has a Tagro. So it's quite a few different cities that do the exceptional Class A. We're probably never going to go to this point where we're going to have have our own brand, and try and sell this stuff. Really, the idea with biosolids is to get it to a beneficial end use without costing us a lot of money, because that's what we do currently, is we spend money to get rid of our biosolids. So I talked a bit about this, about the nutrients. You have all the stuff that the crops want, nitrogen, phosphorus, potassium. You've got a lot of organic matter, so you can build soil structure. So if you have a field that's very sandy, feed it biosolids for several years, and it will help to build up that soil, and it can really improve your crop yields. MSU's done a lot of testing with us over the years, and there is some benefit to that. And it always depends. Every plant's a little bit different, but it is helpful. So you get some good water retention, you can improve your soil structure. Now it has metals. Metals are bad, but some metals are also good. If crops need these micronutrients, they need small amounts of zinc and copper, iron, but it can't have a lot, because we don't want, to cause any sort of toxicity. So we track all of these metals in our biosolids. PFAS, recent concern. We talked about that a bit. We are sampling it. We are tracking it. We stay very up on what EPA tells us is safe to do. So we're going to make sure that our biosolids are going to stay below those levels. Otherwise, we'll have to find a different way to dispose of them. So now we're getting kind of past the background and into the project itself. We talk about the cost. Cost is a huge issue for us when it comes to biosolids. We've gotten up to spending about $1.2 million a year on our biosolids disposal, because even when it goes to a farm field, that farmer may not pay anything for that they'll get it for free from us, but we're paying someone to take it to them. And we have a very large volume of biosolids. So we were making about 5,600 dry tons per year of biosolids before the digester. So that's like 20, I'm trying to remember, it depends on the solids content, but it's somewhere in the realm of like 28 million gallons of biosolids that we had to get rid of. And we only had 2.9 million gallons of storage, so we didn't have a lot of room for it. So we had to split things. We had to send some to a landfill. We had to send as much as we could to land, but you can't land apply year round because when the ground is frozen, you can't safely inject it, and the crops aren't there to utilize it. When the crops are growing, you can't apply it, so it needs to go in between crops. So it was very stressful for us to try and manage the storage and still be able to get rid of the biosolids. So a lot of risk and a lot of costs to come up with that risk. So the landfills, their costs increased. I think I haven't even checked honestly in the last year or two, but it had gone up about 800% what we were paying to send biosolids to the landfill. And a lot of that had to deal with the biosolids that go into a landfill are semi-solid, but they still can kind of flow a little bit. It's more like a clay type material. And there was a landfill out in New Jersey that had one of the cells collapsed on it. And they think the reason was because it had a lot of this, what they refer to as wet waste in it. And the biosolids would be considered wet waste. So they want to limit that. So that has really been a big cutback for us. So we went from paying, $120 per load and then like $18 per ton to spending $1,100 per load. And I think we're at, with fees, it's like $71 or $74 per ton to dispose of them currently. And at the end of the day, too, is when you send these biosolids off to a landfill, you don't have those nutrients are just more or less going to waste. All that organic matter is going into a landfill where it's tied up for forever as far as we're concerned. So the project, we've been talking about this back in 2012 when I hired in. Biosolids have been an issue at our facility pretty much forever, I would say. Even I know definitely since 1974 on when Dave Verhoff started there, for anyone that might know him. But anyway, we really started looking at this in 2017 and we looked at alternatives. What can we do? We didn't want to just say, okay, anaerobic digestion is the only way to go. There's a lot of things out there that can help. So we moved on from there into the pilot testing, the design, construction, and then where we are today, where we are operating, but we're still under startup mode. We had identified 7 different options as alternatives, and they all had benefits. Additional storage, self-performing would be us having our own tractors, our own fields, a lot of work there. And we went through this and we looked at all of them. We looked at what we thought the cost would be for each potential option. We looked at any non-financial benefits we may get, and we really chose with the additional storage and the anaerobic digester as alternatives that we needed to look at quicker, or not quicker, but further, I should say. The pilot testing then, what we went into is we actually ran little mini anaerobic digesters. So that's what these carboys are here on the left side. That was done through a company called BioWorks that partners at Kettering University. So these are done by Kettering University students over in Flint. And then we had a lot of people have probably seen these over the years, but we had more in Bruges Inc. But we worked with, they set up these really nice, layouts so we could try and picture what this was going to look like after it was built. Because there's a lot of concern. It's a tall tank. We're right downtown. There's a lot of considerations to be made. So we got these done. We shared them with the city council, shared them with the planning department, try to see what we can do. So we looked at all of this and we said, yeah, that's, the digester looks like it'll fit there all right. And at the same time, we applied for what's called state revolving fund money, which is a low interest loan program funded through the state of Michigan and the EPA. And the idea is they're trying to encourage municipalities to put in projects. And at this time, they really wanted environmentally friendly projects like anaerobic digesters to go forward. So they'll give you a guaranteed bond with a lower rate than what you would get if you just went out on the market. But also what we really wanted was this 20% principal forgiveness. GPR stands for Green Project Reserve. Now they're not doing Green Project Reserve currently, but at the time they were. So that would say a project like an anaerobic digester produces energy from waste. So that considers a green project. It also reduces the mass of solids going through the facility. So that would qualify for green project reserve. So we ended up getting this and we saved 20%, so about $6 million on the project that we saved by going through the SRF. The SRF also was the alternatives analysis and conceptual design. So these were going on, side by side. And I know our engineer at the time, he put in a lot of work on this and I really appreciate it because it worked out well. The public participation, so we worked with the city of Holland. We brought in Outdoor Discovery Center, the MAC, and we wanted to have a lot of folks involved that have a stake in our facility in this town to really give us input to make sure what we're doing was going to be the right decision. Another big, and I don't want to say the most important thing, but a very, very important thing was cost. Like I said earlier, our costs have been going up very high. The landfill is up multiple hundreds of a percent. The land application had gone up 60%. So the lines are all really tight together, but if you look at the blue and the red would be if we built a bigger storage tank. The blue is no action, which wasn't really an option for us. So you can see that escalates very quickly. We ran it at a 5% escalation rate and 10% escalation rate, because at the time we were going up even more than that. So this really showed us, okay, if we do the anaerobic digester, we can cut down on our solids volume and we can reduce what we have to dispose of at the end of the day, and we can offset our utility costs. So that's really when the anaerobic digester started to shine to us and say, okay, we need to pursue this as our alternative. By going through those two front steps, we're able to say, okay, we do want to do an anaerobic digester. We opted to move towards a Class A product at the end of the day. So we were looking at a heat treatment step, which I'll get into here in a little bit to help clean the solids. We're doing a side stream ammonia treatment, which I'll touch some base on as well, by repurposing our existing structures. We are a very small site, so anytime we build something new, we usually have to knock out something old. So we try to repurpose as much as we possibly can. Now, in the anaerobic digestion process, we are converting a lot, more or less your organic forms of nitrogen are all going to convert to ammonia. And ammonia is odorous. It's a valuable fertilizer, but it is odorous and it's toxic at high concentrations. So that's why we're looking at the side stream ammonia treatment, but also the odor control system expansion. So often I say that's the most important thing that we do is odor control some days, especially given our location immediately next to downtown. So we added a second stage to that. We wanted to utilize our biogas. So we put in what's a combined heat and power unit. I'll have some information on that. And then we utilize reclaimed water on our site as well, which is interesting. For a lot of folks maybe spend time down south or in the Southwest, you'll see purple pipes. I was in Orlando last year and I saw a bunch of these purple irrigation lines running everywhere. They have a lot of it down in like Arizona and anywhere in the desert regions. And what that is it's wastewater effluent that's been purified. And it can often be used for things such as irrigation or makeup water for cooling towers. We use it on our site for irrigation, but also process water. So the anaerobic digester has to be heated and it has to be cooled. We're able to utilize our own reclaimed water to do that rather than purchasing water from the city and putting extra strain on the water distribution system. Because our water plant, especially during the summer months, the usage rate gets pretty high on it. They're running that thing more or less at 100% between Memorial Day and Labor Day. So that's a nice thing that we could do for ourselves even to help out the water folks and keep things functional. Now, the anaerobic digestion process, as was mentioned, is a biological process. It's different from our secondary treatment process because that's an aerobic process, and that's working fast. The water is in one of our aerobic tanks for a matter of hours, maybe 2 to 7 hours based on the flow coming into the facility. In an anaerobic digester, preferably you want to be in there a minimum of 12 to 15 days, and as long as, depending on your digester, it could be in there for 60 days or more. It's because these anaerobes are very slow working. In the anaerobic bacteria, it's the same as like in a swamp or even a lake bottom if there's a lot of muck down there. A lot of us have heard of swamp fires. My wife is from Southern Virginia, and she always talks about the Great Dismal Swamp will catch on fire every now and again. And that's because of anaerobic digestion happening in a swamp bottom, and the methane gas releases out, and then it can catch on fire. But there are 4 main steps to anaerobic digestion, and that's hydrolysis, acetogenesis, acetogenesis, and then methanogenesis. And really what it is you're just converting that organic matter into something that can be consumed by the bacteria, and at the end of the day, it's going to be putting out carbon dioxide and methane. So you can produce a biogas that's around 60 to 65% methane, and the residual of that would mostly be carbon dioxide. So it gets kind of technical with these different steps, but you're kind of going through like an acid phase, so it's going to get a little bit more acidic over time, and then it's going to get less. And it's important when you operate an anaerobic digester that you track all this, because say the acid forming bacteria become too numerous, they can get upset easily. A lot of that will happen if you slug feed an anaerobic digester a bunch of pollutant. I don't know if many of you remember there's a lot of issues with the Lowell anaerobic digester, and they would have these foaming events and the roof would pop off the digester, and it was a mess. It was not good. And really, a lot of what their issue is they were feeding it, it was salad dressing waste. And they were, a lot of it would get dumped in at once, and the bacteria would get upset. And then when they're upset, they'll produce excess amounts of carbon dioxide, and it can foam out and it'll foam over. And if the foam has got to go somewhere, and this one had a flexible roof, so it could pop the roof off of it. I've seen it happen on agricultural digesters as well. They're usually not, I don't want to say that, but they are often not tracked as closely as a municipal one, because the farmers are doing other things, and they don't really have the same permit requirements that we do. So sometimes they'll take a big load of like ethanol stillage, dump it into a farm digester, and if no one's paying attention, the same thing can happen there as well. And you don't want that to happen. You don't want that methane to go into the atmosphere. It's a potent greenhouse gas. It's explosive. There's a lot of reasons to keep them covered. So that went into a lot of our design as well. Because what we really want are these methanogens, the ones down at the bottom, but you have to have all the other bacteria to get it to that point first. Okay. Now, kind of an interesting fact is we did have an anaerobic digester. We actually had 2 anaerobic digesters at our site before. And we're not the only ones. Grand Rapids had a digester back in the 1920s at their plant, and took theirs offline. So in 1960, that's when the plant, as you see it today, was really first built. Prior to that, we were, it's referred to as an Imhoff tank, but it's kind of like sort of like a septic tank, sort of like a clarifier. It didn't do near as much treatment as we do today, but in 1960, we built our primary treatment plant. So we did 2 primary clarifiers, which there's one of them in the foreground, and those primaries are still in function today. The equipment's been replaced, but the concrete is all the same. And the building, which still exists today, it's just been added on to over time. So we had a primary and secondary anaerobic digester, and it worked well enough. We just burned the biogas for heat. They didn't have an electric generator or anything back in those days. And we had a flare that sat right here on the roof. So I have some cool pictures. I didn't have time to include one, but there's some pictures of this thing burning at night. And you can just see this huge flame, It's kind of neat, but not really the look we're going for in this day and age. So these are floating covers. So the covers would move up and down based on how full the digester was. So there's the covers there. And this one is still being used as a tank today that we've converted to our side stream ammonia treatment. So that'll be the tank here on the left. And the one on the right is where we have our odor control now. So that's actually a room that you can walk into with multiple stories. They cleared out the tank and poured a couple of floors in it. That was pretty creative. We did replace it with a sludge incinerator. So this was 72, around the Clean Water Act time, and that incinerator never really worked that well, unfortunately. So by the time 1977 rolled around and we expanded the plant again, it was already decommissioned. It just was kind of a failure. But other facilities were more successful. We had some issues that were probably not thought through well enough at the time, where we added a lot of lime to our primary clarifiers. Lime's not flammable, so it really reduced the volatile portion of our wastewater, so the part that you can burn. By reducing that, it goes into the incinerator, and the incinerator just couldn't do anything with it. But I have seen we removed the incinerator in 2015, but I've seen the exact same ones running down in Detroit. They have like 12 of them, and they've been able to keep them going all this time. But every facility is different. So our digester today looks nothing like the digester did before, nor does it look like many other digesters. However, for any of you that have been over by Granville's plant, which is Baldwin and 196, they have one of these as well, an egg-shaped digester. The egg-shaped digesters are really popular in land-constrained areas. So really big cities would be the most likely place to see them. Manhattan or Brooklyn has, I think, 12 big ones like this. Owl Island, which is Boston's plant, has probably 8 or 12. Hyperion, which is Los Angeles, has a bunch of these egg-shaped digesters, and they work really nice. They're really good at mixing. So the shape is kind of funny, and at the bottom, I'll show you a picture, but it comes down to a cone. It's about, just a couple of feet above the ground. And the pumps and everything are all on the outside of the tank. So you have no moving parts. You don't have to go into this tank for anything, which is really nice. And it's not fun to do. And it also smells horrible. So we'd really hate to be doing that, in April or May. So this really checked off a lot of boxes because we had to remove 2 tanks in order to put this in. So it fit in the footprint. It mixes excellently. It has a small, so at the top it comes together. So that's what we call the gas dome, because all the biogas percolates up through the liquid and is collected in the top. While a smaller gas dome gives it less chance for it to have a foaming reaction. So if those bacteria stay underwater, they don't seem to go as crazy and create all the foam. And we actually have a spray bar up there. So as part of the mixing process, it'll mix that tank and it'll open a valve and it'll spray water on the top, just in case there was any foam to come out. Now the tank, since it's very well mixed too, it stays a little more stable and steady than some digesters would. There are digesters out there, they're called plug flow, where basically you just kind of feed it in and it moves its way through maybe like an S curve or something like that of baffle walls. Those can get, a lot of solids built up in them. They can get, some issues in different areas because different parts of the digester act very differently. This eliminates a lot of those issues. So yeah, I think that's about everything that's really special about this. The company that produces this or built this for CB&I, they also are able to provide the Class A treatment. And I'll hop into that here a little bit more as well, but that's going to be in these darker gray tanks that are to the north of the main gray anaerobic digester tank. So we have kind of a 2-stage system where we're maintaining the large gray tank at 100 degrees Fahrenheit. And that's where we're trying to really encourage the methanogens to do their work. And then in the heat treatment step where we're going to we're not truly pasteurizing, but we're on our way to pasteurization. We heat it up to 150 degrees and hold it for an hour. So that kills off the pathogens that are in the wastewater biosolids coming in. We also are able to scrunch it down a little bit. It is pretty tall, but if you look at Granville's, theirs looks more like, I don't know, theirs kind of comes up more at the top. Ours is really very spherical at the top, and we made that request to try and lower the height. So we're able to cut 10 feet off of it. It's still 105 feet tall, but it could have been 115 if we just let it go the way that CB&I originally wanted to build it. And inside of the tank also it has, there are draft tubes, but those draft tubes don't need anything. They just have nozzles that point into them. And we were looking into this, and Los Angeles has these, as I mentioned, and they took one down after 25 years of running it, and they went inside it and they said they could read the welder's chalk marks on the inside of the tank. It was very, very clean. The tank itself is 1.5 inches thick steel, and it all came in large plates, and every plate was custom bent, so I had a specific spot it had to go. So a lot of welders spent a lot of time out here. For anyone that may have watched it go up, it was pretty impressive. They were out there in February, the wind whipping out there welding. They said that it took 7 passes on each weld to weld it all the way through, and that's on each side. So they're it's pretty wild. They had a machine that would do the horizontals, but all the vertical welds, the welders had to do. So very impressive individuals, a lot of folks from the oil industry that put these together. So they would come in from like Nebraska or Texas or Louisiana. And a wild, interesting way of life. But good. I'm very glad that they put it together for us. The capacity of the systems, we are at 2 million gallons, so this is the biggest one that at least CB&I produces. So when you see the other ones, the large cities, it's just gonna be multiples of the 2 million gallons. So we built it big, bigger than we had to because it was really expensive and we didn't want to have to tear it down and build it again, bigger. So we wanted to make it room to grow. So our goal is for a minimum of 20 years of growth is what we want out of this. And I think we'll definitely be able to make it. You can look, hydraulic retention time is often what you track in these. It's not the perfect indicator of how healthy the digester is, but it's a good rule of thumb. So, if we are at 12.5 days, we're still gonna be digesting well in the future. Right now, we're at 33 days, so we've got, quite a ways that we can grow this. And there's other ways too that we can increase it. We can get better at separating the water out from the biosolids before it goes into the digester. Many different alternatives. But the goal is, make it last as long as we possibly can. So biogas production, we're making quite a bit. We'll talk a little bit about this with the generator, but we're producing between 500 and 550 kilowatts of electricity every hour. So this thing works, and we're gonna be able to go up from there. So that's the idea, is that we might be able to get a megawatts worth of electricity out of this in the future, or we might be able to convert this biogas into natural gas. You can purify it by removing the CO2 and put it into a natural gas pipeline. So they all have their own considerations. And we looked at all the different options before we chose to go with the combined heat and power unit, but anything is possible in the future. Odor control, as I mentioned, is huge for us. It's often like I say, it's one of our bigger impacts with our community is the smell. Wastewater plants, and just due to the nature of what you're doing, there's going to be some odor there. And so we have covered primary clarifiers. All of our solids handling buildings are enclosed, and we have odor control on all those areas. And what that does is we're collecting all the odorous air into one location. And we have 2 stages now. We do a chemical scrubbing, and then we do activated carbon. This is a diagram of the chemical scrubber, which is probably the more interesting of the two. The idea of the chemical scrubber is to remove hydrogen sulfide. That's your rotten egg smell. That's the most likely odor you get from a wastewater treatment plant. And we do this by spraying sodium hypochlorite in a counterflow. So the odorous air goes up, the spray with sodium hypochlorite or bleach goes down, and then here's the reaction that happens. So the hydrogen sulfide gets broken down into sodium sulfate, sodium chloride, and water, and it's no longer in the air, so then the air, when it leaves, doesn't have that rotten egg smell. Hydrogen sulfide is also corrosive and it's toxic. So there's lots of good reasons to collect it and get rid of it. And so you don't need to deal with it at your site. The activated carbon is really nice too, because that will catch mostly everything else. As I mentioned, the anaerobic digester converts nitrogen to ammonia. That ammonia has an odor. The chemical scrubber won't touch that ammonia. The activated carbon will. So it'll absorb it, and eventually the activated carbon, just like a brittle water filter, will be able to absorb no more pollutants. At that point, we'll just have to empty it and then refill it with fresh carbon. And then that carbon usually gets regenerated and it can be reused. But that would be, up to the contractor that does it for us. That looks a lot like it's just a big, FRP fiberglass tank that just sits there and the air flows through it. And then what you do with both of these is you check pressure differentials across like the media in this one, and the same thing with the activated carbon. So that way you know when you need to change it. This was chosen as our combined heat and power. So the biogas, we mentioned it as a valuable byproduct. Flaring it is an option, but we really want to burn it. When I say flare it, that's just burning it, like what we used to do back in the 1960s with no end purpose. The combined heat and power unit is a generator. It's a more or less a natural gas generator that is tuned to run on biogas. And it's in the sound enclosure because it is pretty loud. You open that door and you can really hear it. But outside, it's 50, 60 decibels. It's nice and quiet. So this is very efficient. We can get 93% energy recovery out of this. And it's really because we're recovering the heat. The electricity, we're probably getting a 40% efficiency on, which is pretty high. But then the rest of that we're able to get out and heat, because we need to heat, like I mentioned, the 150 degrees for the first stage of our anaerobic digester and the 100 degrees for the second stage. We're able to generate the vast majority of it here with our combined heat and power unit. Combined heat and power unit also helped us offset. So we're, I said the 500 to 550 kilowatts. Based on the day, that's going to be a third to almost half of our electrical energy consumption at the facility. So that really helps us reduce what we need to purchase from the grid, and allows, that power to go elsewhere or to not have to be generated in the first place. We also have biogas and natural gas boilers as well. As I mentioned, the methanogens want 100 degrees. If they don't get the 100 degrees, they become unhappy and they can get upset, and they could, in theory, die out. So you want to keep it hot no matter what. So that's why we have a backup boiler. We still can burn the biogas in it, but that we don't get the electricity from doing that, but at least we can keep the process heated and we can keep things going there. Another benefit we got from this is we had our neighboring solids handling building's boiler was due for replacement. It was a 2 million BTU per hour boiler. We removed that and we're just running the hot water from this into that building as well. And there are future buildings that we plan on converting over to this biogas heat as their boilers sunset and need to be replaced. So a lot of really good benefits, especially in the wintertime for us. And then the side stream ammonia treatment, I have several different pictures of this through the presentation, but this is that north tank that used to be an anaerobic digester, is now an aerobic digester. And and when I say side stream ammonia, you would say that compared to mainstream ammonia. And in the wastewater, your main flow that comes through and goes through your primary and secondary clarifiers, that's your mainstream. So you can treat for ammonia there, but it's going to be on a large volume. We're taking in about 8.5 million gallons per day of flow right now. So that'd have to be a really big system to treat for ammonia in that. The side stream is just the smaller 60,000 gallons per day we're putting in the anaerobic digester. So by treating that, we can lower that ammonia, and we do that because that ammonia does end up back, a lot of it ends up back into the mainstream. And that's because we thicken it from this point, and that's where it happens. When we thicken it, the water contains a lot of the ammonia that goes back into the treatment plant. Let's see. Here's where I have some of the descriptors. This was the tank as we were building it and adding so basically what it does is, you saw in the last picture, it's looks very rough and foamy. This is a big draft tube and we're pumping air into it. So we're creating an aerobic digester, and you can add air and you can shut air off. And what you do is you drive what's called nitrification, denitrification. And when you nitrify, you convert ammonia into nitrate. So you're adding oxygen to it. So it goes from ammonia, which is NH4, all the way to nitrate, which is NO3. And then once that's done, you basically turn the blower off, and then the denitrification bacteria take over, which then they need oxygen. So they strip off the oxygens until you have nitrogen gas. It goes off into the atmosphere. Our goal is to remove 80% of the nitrogen or the ammonia. And that allows us to ensure we can meet our permit effluent limitations, but we also want to have some ammonia in there because the farmers want this. The ammonia is really the most valuable nutrient to our farmers. So we don't want to get rid of all of it. And in all reality, we really can't get rid of all of it unless we had a very big and very intensive treatment system. Now, it's referred to as a post-aerobic digester. It's not a widely used technology, but aerobic digesters are very, very widely used. Zealand has aerobic digesters at their facility just up the road. So we've anaerobically digested it, we've aerobically digested it, and then we have two alternatives, and that's to either thicken or to water. And that's basically what it's all about. How much water do we remove from the digested biosolids that we have. The top device here on the upper left is a gravity belt thickener, and then the device below it is called the screw press. So we've got gravity belt thickeners and we have screw presses on our site. And the gravity belt thickener is a fabric belt, and you add coagulant and polymers that help flocculate the solids together in the wastewater, and the water will just drain through this belt via gravity, henceforth the name. So it goes on the belt moves across, And there's these plows that you can put down up top here. And it just flips the biosolids over and it causes more water to fall through the belt. And then it goes back from there into the treatment process, ultimately to go out into Lake Macatawa. The screw press utilizes, there's a drum, and this is a big gearbox. The big blue item here on the end is a gearbox. And there's an auger inside of this drum, and the drum is covered in perforation, so small holes. And the flights of the auger squeeze closer and closer together as you go down, and it pushes and it forces the water out. So we refer to that as dewatering, and there's multiple ways of doing it, but this is the way that we have on our site. So when you thicken, you're gonna end up about 5% solids, 95% water. That's gonna go into a tanker truck, it's gonna get hauled off to an agricultural field, and it's gonna get injected with a Terragator, one of these units, that subsurface injects the biosolids under the soil. The screw press is gonna, now that we have the digester, we could in theory land apply this, but right now, if we run the screw press, it goes into a landfill. So this tank is actually delivering to a compost facility, but that way you can kind of see what it looks like. It piles up. So that's about 25% total solids, 75% water at that point. So here I have some pictures that are more detailed of the process itself, so we can kind of see inside and see some of the nitty gritty. Now here's our ATP systems, which is our heat treatment. It's called anoxic thermophilic pretreatment. But the main way I think about it is kind of a pseudo pasteurization step. Everything gets pumped. So we take our solids from our primary and secondary clarifiers, we thicken them up, and then we pump it into this equalization tank. So the tank, if you're, this one's the equalization tank. And then it's going to go into one of the 3 reactors. And those 3 reactors are where we're going to heat it up to 150 degrees. And the idea with having 3 of them is that you can fill one and you can empty one and you can have one that's sitting there cooking. Because when we do this heat treatment, we have to ensure that every bit of that biosolids has been cooked for 150 degrees for 1 hour or 145 degrees for 2 hours potentially. By doing that, that tank is being held, nothing's going into it, nothing's coming out, and you track that temperature all the way through. And then it'll just rotate. So that way you can basically, when we're at capacity, we'll go through all those tanks in a constant fashion, with one of them always being held at temperature to kill the pathogens. We then are going into the main tank that I mentioned, where right now we're in there for 33 days. And that's where the lighter grade tank is the mesophilic stage. And we actually are cooling it. So it's at 150 degrees. We run it through a couple of heat exchangers to lower that temperature to bring it down to 95 to 105 degrees to go into the main tank. Now I'm standing underneath, I'm in the building and I'm looking at those tall, narrow reactor tanks. We've got transfer pumps here and we have recirculation pumps here. And what they're doing is so the recirculation pumps are moving the solids through the heat treatment stage, and they're constantly recirculating, and the transfer pumps are moving it from the equalization tank into one of the heat treatment tanks, and then from one of the heat treatment tanks out into the main digester. I've turned around now and I'm looking south at the bottom of the main tank of the anaerobic digester. So you can see that that cone comes almost down to the ground, and we actually draw right off the bottom of it. So there's really nowhere for the solids to settle out in the tank. So we get excellent mixing. You can see the heat exchangers are all these pipes all the way around the digester. We've got a lot of heat exchangers that allow us to heat up the solids and then to cool it down. In the back, we've got recirculation pumps for the main digester tank. There's 3 pumps that look exactly like the ones that I just showed you, the lighter blue pumps. And they're constantly cycling that, and it consistently will cycle. With the draft tubes, there's 2 separate tubes, and it can either go up and up, it can go down and down, it can go up and down, it can go down and up. And it goes through all that just to make sure that everything is very well mixed and you get a nice homogeneous digestion. Interestingly enough, after we built this tank, before it was insulated, they had to water test it. So they filled it 100% to the very tip top with water, and that tank stretched all the way down that there is a valve here. They had to chip out the floor underneath that valve. It's a little freaky. And then it sprung back, and then it doesn't stretch again. I guess that's something with the properties of the metal. So I'm not afraid to walk under here, so don't worry about it, but it was a little concerning when that was first happening. So now, this is some pictures of our biogas management equipment. So we're coming off the top of the anaerobic digester, and it goes into these treatment tanks here that are on the south side of the anaerobic digester. And this is where we condition the biogas. So we don't take it right off the digester and burn it, because it does have other impurities other than the carbon dioxide. And we don't remove that, but we do remove hydrogen sulfide, because it's nasty stuff. It's very corrosive to equipment. So that's removed in the taller tanks. It's actually removed with an iron media, so it basically absorbs the hydrogen sulfide. And then the smaller tanks are an activated carbon, and their job is to remove what are called siloxanes. And so hydrogen sulfide is from bacterial activity, but siloxanes actually come from personal care products. And what happens is when a siloxane is burned, it turns into silica sand. So in a boiler, it's not the end of the world, but in a reciprocating engine that's moving very fast, it'll eat up the piston rings and the pistons, and it'll destroy it. So that's why we remove that. But if you look at like shampoo or certain, you'll see things in there that say silica in it. Those get converted in the digestion process to a siloxane. Here's our biogas utilization. You've seen the CHP generator, but also we have our two big biogas and natural gas boilers. The one on the left is going to be the biogas or natural gas boiler, and the other one's a biogas or a natural gas only boiler. I'm sorry. The biogas and natural gas boiler, it can be finicky. It took the techs a long time to get settings right, because it has to switch. You might be at 65% methane, or it's going to go all the way up to almost 100% methane for a natural gas. So it took a lot of back and forth, but we got it, and they work really well. I've talked a bit about flaring. This is our flare. Every digester is going to want one, because there is going to be a time when you have excess gas that you need to get rid of. And by burning it, you convert it from methane to carbon dioxide. So it's better for the environment, less carbon intensive. Methane's like 22.5% more potent greenhouse gas than carbon dioxide is. By burning it, you get rid of the flammability issues and then any odors that you might have, and they're going to get taken care of in the flare. This flare is different. It's an enclosed flare, so it has 3 rings of burners, and the rest of it's covered. And that, we just want to be a good neighbor. We've got houses here on the north side. We've got walkways here, a window on the waterfront. We didn't want to have a giant flame going off downtown. We thought it might cause some concern. So we just opted to put this in, and it works really well. This was just another picture of the pad in action, doing its thing. This is while we were filling it up. We do have 3 200 horsepower blowers that feed air to this. Normally, we're either running 2 or 1 based on the treatment needs of this tank. So, touch a little bit on Envision. So we are an Envision verified project, and what Envision is a third-party verification that we built this product with a sustainable framework in mind. So that sustainability is not just environmental, it's also social and economic as well. So that's why we worked a lot with our stakeholders, with the city, with the townships, to make sure that everyone, got to put input on it. We tried to do some things, go a little bit further than what your basic design would be. Things that we would normally do, but this allows us to get credits towards this Envision certification. We ended up with gold as our certification. But some of the things we did is we put a lot of outreach and education. We did our educational signage around the facility for anyone that's walked around it. We've also, like the noise dampening for the CHP, we did pay extra to get more dampening put in, because we didn't want that to be annoying to anyone. We added sidewalk on 3rd Street. We checked our greenhouse gas, and then we've been moving to areas that are not needed for process to moving to native plantings as well. I know that's been going on at our service center and our water treatment plant and at the Holland Energy Park also. Less to mow, and it is nice, brings a lot of good pollinators and such. Here's a picture of our nice Envision plaque. This is a sidewalk we put in along 3rd Street. We have some of the signage around the facility. If you haven't seen it, please go walk around and check it out. This is our additional odor control piping, and there's some of our native plants. And the bottom right's hard to read, but this is the greenhouse gas counting that we did. Currently, we should be able to reach Class A, but we're not. We are reaching a Class B status. So we're still getting to it. The problem is that we're not able to, if we heat the solids all the way to 150 degrees, we can't push enough through to operate. So we actually are heating it now to like 125 degrees, which allows us to meet our throughput, but it does meet Class B standards. So that's why we're still doing the land application on fields, is due to that. The thickening and dewatering, we did have to change our chemical feeds for all of that. When you anaerobically and aerobically digest, it changes the solids enough that the chemicals that we would use to separate the water and the solids no longer worked. So it took us about a year to really find something that worked well, but we have it now. Okay, this is just some more of the benefits. You know, we talked about the breakdown of the organic solids in the digester. Probably didn't talk enough about how much that really did help us. So we're converting 55% of our solids into biogas now, and we're burning it right at our site. So that's, 55% less trucks coming in and out of Holland, 55% less fields we need to use. It's been a huge operational benefit for us and also a huge savings. So we went from, $1.2 million to down, we're about $500,000, maybe a little bit over that after the digester went in, just for that. And we also don't have to add lime. I didn't mention that before, but Tina recalls the lime issues. We used to use lime to stabilize the solids to Class B. We spent $250,000 a year on that also. So that's another savings we have out of this. And then you can add on to that the heat we're generating and the electricity as well. It has a lot of really good benefits for us. For the lessons learned, we'd like to, during our pilot testing, we didn't test everything we wished we had at the end of the day. We didn't check for siloxanes and hydrogen sulfide. So we just had to guess, and when you guess, you over-design. And it's good to be over-designed, but we could probably save some money on the gas treatment system, but nothing major really. Anytime you're in a wastewater plant, if you're digging up an area, you want to get after everything. We had some stormwater lines that I would like to have had moved, but we weren't able to get to it in this project. We had a great experience working with stakeholders and with the public. I think we looked at the color of the digester, that can always be a really questionable thing. I know I had lots and lots of questions, especially when it was red and rusty. I was very happy when they finally got a color put to it. We always need to be flexible with our operations. The Envision process, I'm glad we did it, but it took a lot of work. A lot of work, and it was rather expensive to do. So I would only recommend that we would do that for our big projects, but we'll still follow the same tenets of that because we do want to be sustainable for our communities. And then power factor, a lot of us probably don't know about this, and I didn't really either until this happened. But when our generator turned on, the power factor is more or less how efficiently you use electricity from the grid. When the generator came on, it threw that off balance. And it actually reduced our efficiency, even though we were producing electricity. And it was because we reduced the amount of power we bought from the grid, but we still bought the same amount of variance, or VAR, they call it. So it cost us a fair amount of money because we went so low that they start to fine you because they need you to improve it. But we got it fixed. And now we're up to well over 0.9, which is where you want to be. So we're over 90% efficient in the power that we are purchasing from the grid. We're cognizant of time here. We will be our next step. So we still need to work through some of these heating issues, but we have a plan. We're working on it. I'm sure we will get there. And once we have that, we can finalize our Class A designation for our biosolids. Our polymer coagulant issues are mostly resolved now. I talk about Ottawa County a little bit because we are working with other wastewater plants in the county and the county themselves at a potential regional facility that all of our biosolids could, in theory, go to. I'm looking at some different technologies for that, trying to figure out, similar to this project, is whether or not it makes sense to do so. And if it does, then we'll move forward. But as of right now, nothing further there. And then, yeah, we look to optimize our gas utilization. We don't wanna waste it. There we go. Happy baby.
Yeah.
Okay, I think I'm pretty good info.
Are there any questions from you? Hold on a second.
Yeah.
What did you ask?
I was curious what the cost. total
Sure.
cost.
The project budget is $33.7 million. We'll be below that, so it'll be around 33 million or so, but we got 6% back from the Green Project Reserve. And fortunately, we actually were able to utilize the Inflation Reduction Act funding as well, and we got $10.5 million off on that. So this is actually a pretty affordable project. And the cash flow worked out really nice, even at the full price, just because we knew that the solids disposal was getting to be so expensive.
It wasn't obvious, great presentation, but it wasn't obvious, once you had this big, beautiful tank, painted the right color, and all those pipes and pumps and everything else, and you start putting stuff in it,
Mhm.
do you have to go to the anaerobic bacteria store? and
Sure.
take some
It's a good-
seed stock?
That's a great question.
For what?
Yep, yeah, very good question. So all of the bacteria in the process are there, but at very low levels, even for our aerobic bacteria. So you don't want to start from scratch if you don't have to. So we actually seeded this anaerobic digester. We went to the city of Granville because they've got a very similar anaerobic digester. And we took 200,000 gallons of their digestate and put it into our anaerobic digester. So then once you've got that amount of bugs, they just go nuts and they're ready. But if you wanted to start from scratch, it would take months to grow them otherwise.
With bread and
Indeed.
stuff.
Yeah.
So along those lines about the bacteria, how many different strains of bacteria do you have there? Because they actually do different purposes.
They do. Yeah, and I'm probably not the expert to speak to that, but I know there's a lot. There's at least the 4 different types that take you through the 4 stages. The acid forming, the acetogenesis that's doing more of the acetic acid, and then the methanogens, but those are the most important ones, are the methanogens. And not all of them are bacteria, some are archaea as well. For any of them that are familiar with that, but I know when I was in college, I got corrected by that by my professors all the time, that it's not just bacteria, it's archaea as well. So lots of different things. There are also a little indicator organisms, so there are some small single cell organisms you can look at. So we will put those on and look at them to see if it's healthy or not. So we actually have a microscope that we can look at our solids with, but you're not going to be able to see the small bacteria at that point.
These colonies of bacteria operate most efficiently under certain pH and temperature conditions.
Correct.
So as the nature of the slurry changes, what does the pH change, and do you need to adjust it?
Sure. So when we are balanced, it's going to get more acidic and then less. So you'll build alkalinity in an anaerobic digester. Our anaerobic digester actually operates at almost too high of a pH, which is not normal. It's actually around 8.4. And that's because it's oversized right now. It's in there for so long. So when we go to our aerobic digester, sometimes we actually have to add acid to it to bring the pH down. Usually we're worried about the opposite, where it'll be too acidic and we need to make it less, more basic. So yeah, we do track that, but we also track the wastewater. So the part of the industrial pretreatment folks' job is to track pH as well. So we need to make sure that the sewage coming to us is at a certain pH. And there are chemicals that we add to the process, like we use ferric chloride, which binds with phosphorus in our mainstream. If you add a lot of that, you will bring down the pH of the entire plant, and that could be, in theory, problematic.
Indeed. Question.
I was just wondering, I know you're not up to speed, but are you still researching whether you might be able to take extra organic waste from some of the companies, that food processors we have around here?
Yes, we are. That's been a very popular question to us. A lot of the food processors have to pay a lot of money to pre-treat or haul away their solids. So we are looking at that extra right now. They're referred to as tactical actions in our organization, but it's kind of a special project. And we're heading up one right now we have this excess capacity. Could we use it beneficially to help out some of our customers and save them some money, and for us to produce more biogas as well?
Question here.
Yes.
Batch by batch, as you handle this stuff, there's differences in makeup of the batches. You have to change the inoculation of the bacteria as you go from batch to batch. If so, how does that take place?
Sure. So the thing with the anaerobic digester, as you mentioned, is that things do change over time. So we need to limit those changes. Our sludge or solids, they will change over time, but not by a lot. And that's generally due to work with like our industrial customers. So as the solids don't change too much on the incoming influent, it's not going to change too much in the digester. So what we do is we actually track, so I mentioned the days of retention. Well, we track more than that. We track volatile fatty acids and alkalinity. And that ratio will tell us how healthy the bacteria in the digester are. So we're tracking that every day. And if it starts to get too wonky and the digester gets too acidic, then we know we need to make some
The other
differences.
question I had, how do you handle heavy metal?
So,
So we first presented coolant stuff,
sure.
they could have microparticles
Mhm.
of brass, of copper, of steel, of chromium, of barium, of vanadium. How do you handle all that stuff as it comes into your plant?
So that's where we work with the source on that, because we can't treat for heavy metals. We're not built for it. So our sources are able, if they do have the issue, they either collect it and haul it away for specialized treatment, or they will purchase and run their own like chemical treatment to precipitate out that metal before it comes to us.
Generally, you combine it with something else, with a bond together, and then they centrifuge it out.
Mhm.
instead.
Yeah, we do have customers that do that currently.
Any other questions? Yes.
First of all, what a great presentation. Wow.
Thank you.
This
Yeah.
is really exciting. Can you give us examples of what the human pathogens that you filter out of the system are?
What they could be, sure. A lot of the ones that we hear about are the ones that we're most focused on. So it'd be like your diphtheria and cholera and things like that. We don't have that here, but it could, right? And that's how it's spread. It's usually through water. And you hear about this in like third world countries or developing countries, I should say, where they don't have the treatment on the drinking water side or the other. So those are things. There's other ones that, it's hard to say. There's a lot of fecal coliforms. So E. coli, that's a big one. That's one that we actually do test for quite a bit in our biosolids. So yeah, they're there. There's probably a lot more that I'm not thinking of right now, but we're trying to hit all these big ones to make sure that we're not going to get any sort of like water-based outbreaks of illness. Yes.
One other question. City of Holland is growing, rooftops are growing, new businesses are coming in. What percent of capacity are you at now?
So our digester, we've got over 50%. We can grow on that. Where we're going to run into constraints will be on our main treatment plant before that. So we've expanded our facility. We're probably maybe, flow wise, we're pretty high. I think we're like 8.5 to 9 million gallons per day. We can treat 12 million gallons per day of flow, but on certain pollutants, we are a little bit closer. So we're 60 to 70% on certain ones. But we did do an expansion back in 2016 that gave us, I think, another 30% of our compatible treatment on our east plant. So we are looking at this. We're looking at options for what would we do next. So we do come up against that. And that could be anything beyond building out our plant, adding more tankage, or potentially even building a second treatment plant somewhere in our collection system, maybe on the north side or on the south side. So we do track that. We're not... Some months we'll be at 80% on our phosphorus, but for the benefit of treating phosphorus is we more or less just have to turn up our ferric chloride feed. It's our biological and solids, that stuff, we have to have more tankage if we're going to remove that. And that we're sitting pretty well on currently. I don't have any immediate concerns with that, but we do watch it. I've got a report that generates quarterly and it tells us how much capacity we have left for industrial customers, and out of 55,000 pounds per day of biological oxygen demand, I think I have 20,000 available for customers to use. So we are open for business, but we'd really like to not expand if we don't have to, because that's very pricey.
Any other questions? If not, we thank you for a very informative.
Well, it's been my pleasure. Yep. Yep, Zealand, they just expanded their plant in
Yeah.
2017.
I know, but
They doubled in size.
they get.
They do an aerobic digester in Zealand. So it's similar to that side.
By the time.
The flyer is actually Zealand Farm Services.
All this stuff. Down to like an $11 million program, you know. And How well, yeah.
Water system. What's a valid point? Yeah, I absolutely do. So sometimes if you're in an old home, you know, you can have like biking. Oh, that's very nice. Yeah, my house, I have, when I right now, get over at it. You know, talk about running up. They do a lot of testing. Yeah. This one's really good water.
I just.
Yes, now it's getting good system, yeah.
Oh, hey.
And I haven't heard my name for 6 months. Yeah.
So Dave does.
Yeah.
He swear.
There's to, no.
He's probably.
Yeah, he put the tires.
Yeah. Well, shit, tell me.
I will.
My last year in college, we had a house. Good.